Welcome to our video on efficient parallelization in Python. In this first part, we'll explore the foundational concepts of parallelism and concurrency. So what is parallelism? It's the ability to perform multiple tasks simultaneously, while concurrency is about managing multiple tasks at once, which may or may not run simultaneously. In Python, understanding these concepts is crucial, especially due to the global interpreter lock, or GIL, which allows only one thread to execute at a time. This can be a bottleneck when we want to run CPU-bound tasks in parallel. But why do we need parallelization in Python? The answer is simple: to enhance performance and efficiency. By utilizing parallelization, we can significantly reduce the time taken for tasks like data processing, web scraping, or any I/O-bound operations. As we progress through this video series, we will dive deeper into multi-threading and multiprocessing, demonstrating how to implement these concepts effectively in your code. So stay tuned as we unlock the potential of parallel programming in Python. Now let's talk about multi-threading in Python. Multi-threading is particularly useful when dealing with I/O-bound tasks, such as network requests or file operations. You might wonder, when should you use multi-threading? If your application spends a lot of time waiting for external resources, multi-threading can help you make better use of that idle time. Python's threading library provides a simple way to create and manage threads. For example, consider a scenario where we need to fetch data from multiple web pages simultaneously. By using threads, we can initiate multiple requests at once, rather than waiting for each one to complete sequentially. However, it's important to be aware of potential pitfalls like thread contention and race conditions. These issues arise when multiple threads try to access shared resources, leading to unpredictable behavior. In the next part, we will provide a practical example of how to parallelize I/O-bound tasks using the threading library, ensuring you avoid these common traps. Moving on to multiprocessing in Python, this approach is ideal for CPU-bound tasks. So when should you opt for multiprocessing instead of multi-threading? If your application is performing heavy computations that require significant CPU resources, multiprocessing is the way to go. Python's multiprocessing library allows you to create separate processes, each with its own Python interpreter and memory space, thus bypassing the GIL limitations. For instance, if you're processing large datasets or performing complex calculations, using multiple processes can drastically improve performance. It's essential to understand the key differences between processes and threads. Processes are independent and have their own memory, while threads share memory space. This leads us to another important concept: shared memory versus message passing. In multiprocessing, you often use queues or pipes to communicate between processes. In our next section, we'll dive into practical examples of parallelizing CPU-bound tasks using the multiprocessing library, demonstrating how to maximize your code's efficiency. In this part, we'll explore how to simplify parallelization using the concurrent futures module. This higher-level API provides a user-friendly way to manage threads and processes. The two main classes you'll encounter are thread pool executor and process pool executor. These allow you to easily execute tasks in parallel without delving into the complexities of thread management. One of the major benefits of using concurrent futures is its simplicity. For example, with just a few lines of code, you can submit multiple tasks and retrieve their results as they complete. Let's consider a practical example. Imagine you want to download images from several URLs concurrently. By using thread pool executor, you can create a pool of threads that handle each download task, significantly speeding up the process. In our next slide, we will implement a simple parallel task executor using this module, showcasing how effortless parallelization can be in Python. As we delve into performance considerations and optimizations, it's crucial to measure the impact of parallelization on your code. Using tools like Time and cProfile, you can profile your applications and identify bottlenecks. When deciding between multi-threading, multiprocessing, or even other libraries like joblib, consider the nature of your tasks. For I/O-bound tasks, multi-threading may be sufficient, while CPU-bound tasks will benefit more from multiprocessing. However, common mistakes can hinder performance, such as poor load balancing and inefficient task splitting. It's essential to manage resources effectively to avoid overwhelming your system. In our next section, we will discuss best practices for structuring your Python applications for parallel execution, ensuring you harness the full potential of parallelization without running into performance pitfalls. Finally, let's discuss best practices for implementing parallelization in your Python applications. Structuring your code for parallel execution is key to achieving optimal performance. Start by identifying tasks that can run concurrently and consider how to divide them effectively. Scaling up parallelization to handle larger tasks can also improve efficiency, but be mindful of resource management. Additionally, debugging parallelized code can be challenging, as traditional debugging tools may not work as expected. Use logging and profiling to troubleshoot performance issues effectively. To illustrate these concepts, we'll look at a real-world example where a data processing application was optimized using parallelism, leading to significant performance gains. By applying the techniques we've discussed throughout this series, you can dramatically enhance the efficiency of your Python applications. Thank you for joining us on this journey into parallelization in Python.